Have you ever wondered how clothes in the future will be? Hello, I'm Sylvia and I will talk about an intelligent knitted textile with polymer optical fibers for friction and pressure monitoring in socks. For several years, smart textiles have been a fast growing development, and there has been an increased market for these materials. In these textiles, optical fibers can be integrated as sensors for various applications in the medical field, such as monitoring and therapy, making possible the measurement of physiological parameters or specific activities by wearing normal clothes without causing discomfort. Some concepts needed to understand this work are that irradiance is the radiant flux or power received by a surface per unit area. From all kinds of electromagnetic radiation, it gives the power density at a particular wavelength. A polymer optical fiber is a type of optical fiber composed of a core generally from polymethyl methacrylate or polystyrene that allows the transmission of light, and the cladding made from fluorinated polymers. But how does a POF work? Light travels inside the core by bouncing off the walls of the fiber repeatedly. The cladding is the external layer responsible for the light guiding effect, which forces light to travel through the length of the fiber.
The methodology of this article is direct. Light is introduced. The power transmitted by the fiber, with or without deformation, in this case friction and pressure, is measured to calculate the relative losses. Both criteria must meet that the power must be high enough to be recordable with the available sensor, and that small deformation changes have to produce notable changes in losses. This is the sensitivity criterion.
Now, referring to the procedure, they started with the POF selection. In this case, polycarbonate and polymethyl methacrylate fibers were avoided because the researchers were looking for a flexible POF with low bending rigidity, which depends on the Young modulus E and the moment of inertia of the cross-section I, and for a circular fiber it's calculated by this formula, where D is the diameter of the fiber. They selected the following options from different polymers: a GigaPuff 50 star made with a perfluorinated polymer with a core diameter of 50 micrometers and a cladding of 490 micrometers; a bicomponent fiber made of a cycloolefin fluorinated polymer with a diameter of 144 micrometers; a monocomponent fiber using a Genuine 100 polymer with a diameter around 824 micrometers. These POFs went to tensile and bending characterization. Tensile tests were carried out using an MTS tensile machine with a sensor of 2 kilonewtons and a speed of 500 millimeters per minute. They obtained the following load strength plots. The bicomponent POF has the lowest tensile properties. The GigaPOF fiber broke at the beginning, also the cladding showed higher tensile properties. The monocomponent POF exhibited the highest level of elongation, so despite its higher diameter, it's less rigid. For the bending properties, a normal tension of 1.6 centimeters per textile was applied on the yarn during the knitting process. They calculated the Young modulus and the bending rigidity with the first formula. The monocomponent POF had the best elastic deformation and the lowest bending rigidity. Therefore, it was selected for the intended application. An industrial flat knitting machine was used for the ground yarn made of classical textile fiber. 3 basic knitted fabrics were obtained: a single jersey composed only of 1 face stitches, a 1x1 rib, and a 1x1 interlock, which has 2 sides, face and reverse stitches. The puff was inserted into each knitted structure by wedging it between the wales of the stitches, or what is called inlay yarn, to avoid a loss of the light signal at the output of the fiber. The fabrics were analyzed and one of them was selected to determine whether the monocomponent puff was able to measure the pressure and friction during walking.
The compression test consisted on applying a cyclic normal load to the optical fiber. For friction test, and a normal and tangential load on the optical fiber were applied, with a sliding distance of 30 millimeters perpendicular to the puff. and the sliding speed of 20 millimeters per second was used. All processes were carried out in a tribometer.
In order to have reproducible results, measurement was performed on 5 samples for each normal load and was repeated 5 times for each sample. Each test also involved 5 compression-friction cycles, meaning that for each normal load and each configuration, 125 measurements were performed. For light measurement, an halogen white light source was connected to the friction and sample setup. The measurement of light relied on the light transmission through the optical fiber, which only depends on the fiber deformation due to pressure and friction, and the irradiance was recorded and converted into voltage by a photodiode connected to a pulse data recorder, and by using the following formula, irradiance loss was calculated, in which the irradiance loss percent is the maximum irradiance minus the instantaneous irradiance divided by the maximum irradiance per 100. The values vary from 0 when there is no loss of light to 100% when no light is transmitted through the puff due to the applied stress. It's important to mention that the measured values of the evolution of irradiance loss relative to the normal applied load and the evolution of the irradiance loss relative to the tangential load for compression and friction were set in plots to analyze the results. The higher the percentage of irradiance loss, the greater its sensitivity to the impact force, which provides greater accuracy while sensing friction and pressure.
For compression and friction, the experimental curves were fitted with second-order polynomial trend lines, which are the dotted ones, and the equations of the fitting curves are given by this table.
The single jersey presents the highest values of irradiance loss, and therefore the highest sensitivity. This may be due to the fact that this fabric was the thinnest. The optical fibers in the single jersey are more stressed in compression than the optical fibers within the 1-per-1 rib or the 1-per-1 interlock fabrics, since in these structures the optical fibers are more protected because of the number of sides. For friction results, we have one plot for one normal force applied and one another for tangential load. The irradiance loss increases with both forces, and the single jersey shows the highest sensitivity. During the procedures, when the fabric moved, the optical fiber followed the movement of the knit, causing a large deflection of the puff that modifies the path of the light inside the optical fiber and has an impact on the irradiance loss. But optical fibers of the single jersey fabric are more supported, meaning that their movement inside the structure is less significant. For all these reasons, the system was chosen to knit the sock.
To measure the pressure and friction during walking, 3 optical fibers were inserted at 3 different foot pressure zones inside the sock: heel, midfoot area, and metatarsal area. To identify each zone, an accelerometer was put on the shoe to synchronize with the puff signal. The starting point was determined by a video to correspond with the moment when the foot leaves the ground. A volunteer was selected to wear this system while walking.
They obtained one plot to show the evolution as a function of time of A. The acceleration signals, and B. Light signals during walking at 2 km per hour. For puffs, placed at different positions under the foot and the corresponding step of the walking gait. According to the results, irradiance loss is the highest when weight is applied to the optical fibers. Moreover, the 3 optical fibers show different types of light evolutions, meaning that it's possible to differentiate the fiber position from the irradiance signal.
In conclusion, the optical fibers were inserted by inlay inside 3 different knitted fabrics, and these structures are sensitive to both compression and friction. The sensitivity is higher on the friction test, when normal and tangential loads are combined. The single jersey exhibits the highest sensitivity, and therefore it was used to knit a sock for pressure measurements while walking. The results show that the optical fibers allow a walking gait to be maintained and measure the stresses acting on the fibers in different zones. That's all. Thank you for watching, and you can check all the references here.